This is a facility located in Denver, Colorado, in a nondescript building. And it's cold storage, very cold, lined with a whole bunch of these metal canisters like you see pictured here. And inside every one of those is ice that looks like this. This is an ice core, and these come from land ice in places like Antarctica or Greenland, where researchers go down and they drill down into the ice, which can be extremely thick, miles thick in some places, and they pull it out as a core like this, and you can see it's made up of layers. And those layers are just like the rings of a tree. Every one of those is 1 year. For the specialists in the crowd, actually every 2 of them is 1 year, because there's like a light one and a dark one because of the seasons in Antarctica, but technicality. Every one of those has a really important record in it, because the reason there's these layers is snow falls in Antarctica, and it doesn't melt, really, it stays there, and then more snow falls on top of it, and more snow falls on top of it, and just gets packed down and forms ice with a record each year. But inside that ice, just like an ice cube out of your freezer, there's little bubbles of air. That air, kind of blows my mind to think about it every time I do, is the actual air that was on Earth when that snow fell. And this goes way back in time because the ice is so thick. The deepest ice cores go back 800,000 years. So we have the actual air from every year going back 800,000 years. And you can sample that air, take measurements on it, and get the exact concentrations of what the atmosphere was made up of every single year going back that far. You don't have to guess, you don't have to project, actual air. So these are the data just from the last 1,000 years. I'm not going to show you all the 800,000. And what you notice is the concentration of carbon dioxide in our atmosphere was just kind of moving around through a pretty narrow range year to year. Those variations have to do with things like just natural subtle shifts in the way the Earth orbits the sun and the tilt of the Earth and so on. But then something happened in the 1800s. And what happened in the 1800s was us. We started burning fossil fuels at a much greater pace than previously. And when you burn fossil fuels, it releases carbon dioxide into the atmosphere. And so not surprisingly, the concentration of carbon dioxide in the atmosphere goes up. And there you can see it. It started climbing. So that was one data point every year. Starting in the 1950s, though, we started using modern scientific instrumentation to actually just directly measure what is the concentration of carbon dioxide in the air, today and each day. So there are observatories around the world that do this. One of them is in Hawaii. That's the one that's pictured here. And so we have not once per year data points. We actually have daily data points now going back from 1958 until today. That's what the data from that observatory look like from 1958 until today. You'll notice it's continuing to climb over time because we're still burning fossil fuels and putting more carbon dioxide into the atmosphere. One just interesting piece of trivia is you notice when you get daily data, there's a wiggle on top of the overall trend. It's winter always somewhere, right? Between northern and southern hemisphere. The difference is there's just more land mass in the northern hemisphere than there is in the southern hemisphere. It just so happens on Earth. So the natural cycle of plants, they grow in the spring and the summer. They suck carbon dioxide out of the air as they're growing. And then in the fall and winter, as they die off, they release that carbon dioxide back. And so it just gives you this cycle. It's the Earth breathing, which I think is kind of cool to think about. But all it does is add a wiggle on top of the overall trend. The overall concentration doesn't get changed by that breathing. It's us changing that concentration. Now, if I take those two plots and I put them on the same scale, you can really see what's happening here, right? We are extremely increasing the carbon dioxide concentration in the atmosphere relative to what it's been for a very long time. It hasn't been this high in millions of years on Earth, where we are today. And so carbon dioxide is a greenhouse gas. You add more to the atmosphere, we warm up. There's global temperatures up there. They've been rising. If things warm up, ice melts, land ice is melting, sea level is rising. These are all expected trends that you would get as you put more carbon dioxide into the atmosphere, and there's the data. Despite all the kind of noise you hear out there in the general discussion about, oh, scientists aren't sure and the trends aren't clear, pretty clear what the trends are. So I want to walk through this kind of line of cause and effect, and then we're going to kind of work our way back through it again. So we're emitting carbon dioxide into the atmosphere. That increases the concentration of carbon dioxide in the atmosphere. Because it's a greenhouse gas, that leads to warming. And what we really care about is that that warming has consequences. It's not benign. And I'm guessing if you came to this talk, you probably don't need more than one slide, so I've only got one slide on consequences. High level, these are the types of problems that we are already encountering today and will certainly encounter to a much greater degree in the future. It's a problem. I didn't used to have this slide at all. I gave this talk to a bunch of state lawmakers recently, and I just assumed everybody assumed this was a problem. Not everybody assumes that, so I threw this in here even though I know you guys already know this. Okay, so what are we going to do about it? There's basically three categories of things we can do about this: mitigation, geoengineering, and adaptation. And we're going to talk about all of them. I'm going to start with adaptation. So what adaptation is about is trying to soften the link between the warming that's happening and the consequences that we and everything else on Earth is experiencing. So how do we soften that? We can do things like, if you're worried about sea level rise or increased storm surge, you can build seawalls in our coastal communities to try and mitigate some of the damage that will happen as the sea encroaches on you or a big storm surge comes in. We can make our infrastructure more resilient to the extremes that we're going to have in temperature and precipitation and so on. We can reinforce our electrical grid and our water infrastructure and so on to accommodate some of the stresses that it's going to encounter. We can have better disaster response because they're bigger and more severe disasters. And in some cases, we can actually move people away from the regions where it's going to get really, really bad. And I read a great book earlier this year that I'll just give a little plug for, The Great Displacement, which is basically about how this is already happening here in the United States. And he documents really nicely through very personal stories about individual people and their experiences, how entire communities have already been uprooted because of the things that are happening here. So those are all things we can do to try and adapt to the changes that are happening around us. But it's really important to understand that we cannot adapt our way out of climate change. The changes are too big, too fast. There's no level of adaptation that can save us from suffering from these consequences. So that's why we're looking at other options. And this is an option. I've been giving talks on this topic now for probably 15 or more years, and this was like crazy stuff back then. Very, very few people were seriously talking about this topic of geoengineering back then, and it tells you something that now it's mainstream conversation. So what is geoengineering? This is deliberately changing the planet in a way to try and counteract what we've done. We've actually geoengineered already by accident. Putting all the carbon dioxide in the atmosphere was geoengineering. We didn't know it early on, but now we know it. So that was an inadvertent geoengineering. The idea would be to do intentional geoengineering to try and undo some of that. Now there are two kind of broad, there's lots of ideas people have for geoengineering, but they fall into basically two buckets, and I'm going to address them separately. One of them is trying to reflect sunlight, have less sunlight, get down here onto the surface to warm things up. That's where the heat is coming from in the first place, of course. So that would be a strategy. And there's various ways you might do that. The purpose of this strategy, which I'll call solar geoengineering, is to soften that link. It has nothing to do with how much carbon dioxide is in the atmosphere. It's all still there. But we're trying to soften the link between that concentration and the amount of warming that actually happens as a result of it. That's solar geoengineering. So you can see we're working our way back from kind of the consequences back to the root here. And this is kind of the idea of solar geoengineering. So temperature over time, the white curve would be kind of where we are. It's going up. I showed you the data, but this is just an approximation of that. And today, we're somewhere below what I'll call the stabilization temperature, where if you pass that temperature, there's no coming back, at least not in the lifetime of humans on Earth. So we do not want to cross that line. Exactly where that line is a topic of debate and discussion in the research community, but it exists, and we're approaching it. The concern is that even if we take very aggressive action to put in more solar panels and wind turbines and all the things that we realize we need to do, we're not going to be able to do it fast enough to avoid crossing that line. That would be this green curve where we're going to cross it, And then we would come back later, but you can't come back later is the problem. The idea of solar geoengineering is to buy time. So during that window of time, a few decades, however long it needs to be, while we're transitioning off of fossil fuels to renewable energy and so on, we need to prevent warming so it doesn't get too warm. Solar geoengineering is a way to do that. It's like artificially cooling us down for a little while just to buy us time to get the technology out there to try and address what needs to happen. Now, that's the idea, but it's scary, right? We're talking about planetary scale things, right, to reflect sunlight. I asked DALL-E, the AI, generative AI graphics thing, to make me a steampunk weather machine. So this is what it made. That's kind of what I imagine are just giant machines pumping out, sulfate aerosols or what have you into the stratosphere is one of the examples. It's pretty crazy to think about, but very serious people are taking this very seriously. This is just from this month. James Hansen, for those who follow climate change, know that name. He's one of the most famous, if not the most famous climate scientist, testified in front of Congress in the 1980s that we're creating a problem. So certainly a thought leader in this domain. And he just published a paper this month where he's now convinced we need to do this. He says it is a required action to intervene with the Earth's radiation balance with geoengineering. That's a big deal when James Hansen says that. But this is scary, and there's surely going to be unintended consequences if you were to try such a thing. And that's why other thought leaders, like Michael Mann here, he's the guy who first published the hockey stick data, the kind of like what I showed you at the beginning. Another very smart person who has tremendous experience here, he's kind of on the other side. He's like, this is too dangerous. We're not sure exactly what's going to go wrong. You may not be able to stop once you start, or else the warming all kicks back in because it's all basically artificial cooling that you're introducing. So this is being hotly debated right now. But again, it tells you how serious the problem is that this is the conversation that's happening. The other category of geoengineering is getting the carbon dioxide out of the atmosphere, removing carbon dioxide. So literally undoing what we've done by putting it up into the atmosphere. And there's various ways to do that, but I'm going to just talk about specifically capturing it from the air, so-called direct air capture, and sticking it away somewhere. So what is carbon removal about? It's about breaking this link. So it's not changing our emissions. We're still using the fossil fuels, still producing emissions, but we're trying to not have such an impact on the concentration of carbon dioxide that's actually in the atmosphere. I happened to take a vacation to Iceland with my wife earlier this year, and I asked her to divert off the highway near Reykjavik so we could go to this thing and I could take a look at it with my own eyes. This was, and I think will very soon be surpassed, the largest direct air capture plant on Earth. And it's in a great place in Iceland because they have geothermal energy, so it's powered completely by renewable energy. It runs air through those big fans, captures the carbon dioxide, and then sticks it down in the ground where it mineralizes and forms essentially permanent rocks down below the surface of the Earth. Works great. And that thing captures about 4,000 tons of carbon dioxide every year. Now, that was a good first demonstration. The Department of Energy just very recently has announced 2 very large projects, investing more than $1 billion to build 2 plants here in the United States to do kind of what that Orca plant does in Iceland at a much larger scale. When these plants are online and up to their full scale, between the 2 of them, they will capture 2 million tons of carbon dioxide a year. That's our global emissions of carbon dioxide every year. So that's a more than $1 billion investment. It's not even there yet, and you can see not making a dent. You would need 40,000 of those hubs just to offset what we're pumping out into the air every year with our emissions. So daunting scales involved here. So this is what I like to think about when we're trying to deal with climate changes. This trucker ironically discovered on the road to success there are no shortcuts. So this brings us to the final kind of set of approaches, which is mitigation, dealing with the emissions themselves. And there's another type of not carbon removal, but carbon capture that can certainly help here, so-called point source capture. So one of the challenges with direct air capture is that carbon dioxide is actually very dilute in the atmosphere. It's 400 some parts per million. That's not a very high concentration, so it's really hard to get it back out separated from all the nitrogen and oxygen that makes up the atmosphere. But why wait until it's all dilute? Why not just capture it right at the pipe of the power plant or the tailpipe or what have you, right at the point source where it's much more concentrated, takes much less energy to capture it there, a lot smarter than trying to pull it out of the air, although we're going to have to do that at some point regardless. So point source capture is smart thing for us to do. It will make a difference. There are a number of point source capture plants already in action around the world, a number of them right here in the United States, including some of the largest ones. These are already larger scale than the direct air capture hubs are going to be. But you can add all of those up, and that's 43 million tons a year. All of the plants in the world today, that's what their capacity is. Again, that is not even making a dent here in terms of the total emissions. So the scale that's required is astronomical if you want to use this as your solution. So clearly, the only real solution here is to kill this thing at its source, which is to stop emitting so much carbon dioxide. It's about decarbonizing our economy. And so how do we get into this mess? It's all about energy. This is a plot of energy use around the world. The units on the y-axis are terawatts. That's trillions of watts. A lot of energy. Well, rate of energy use, to be more specific. And these are actual data. I have data on here up through 2020, and it's projections going forward. So it's still pretty current. One thing you'll notice is that we keep using more energy over time. That's not going to stop anytime soon. You can see the projections here have it going up to the year 2050, increasing even more beyond that. So we need more energy every year than the year before. Another interesting thing when you look at these data are you can see how closely energy use is coupled to just kind of global productivity. Because you see a couple times when it didn't go up. There was a little blip down. And we're in the boost school, so you guys all know what happened in 2009. Great recession, global productivity shrank, energy use went down temporarily, and then right back up. Next dip, pandemic. Same thing, but again, right back up again. And what is our energy mix? So those three shades of gray are the fossil fuels, coal, oil, natural gas. You can see that's where almost all of our energy is coming from, with relatively small contributions from green, which is all the renewables put together, and the kind of pinkish purple there is nuclear. But what you might not have realized is that the projections going forward are not less fossil fuel use. I mean, I just told you what a problem we've got, right? That this whole thing has been created by burning fossil fuels. The projections are not that we're going to use less fossil fuels, but that we're actually going to use more. It's insanity, right? This cannot be the energy mix in the year 2050. What we need is that low carbon piece, the renewables and nuclear in some combination, need to be way bigger. So sure, they're going to grow in the projection, but that's not enough. That slice of the pie, if you will, needs to look something more like this. It needs to be the majority of our energy coming from these low carbon sources. I say it's got to be at least 20 terawatts out of the 30 or 31 that we're going to need. Even more, of course, would be better. So where are we going to get this energy from? Here I've got boxes that I've scaled in size to represent approximately how much energy it's feasible to get from these different energy sources if you did it everywhere you could in the world, where it actually makes sense. So fossil fuels, you can power the whole planet on fossil fuels. That's more or less what we're doing today. We could keep doing that. You know, the stories of the end of oil, that's not the story. There's plenty of oil, and there's certainly enough natural gas and coal for a long time. So we're not going to run out of these things. We don't want to wait. You know, there's that great quote from a Saudi oil minister: "The Stone Age didn't end because we ran out of stones." We can't wait until we run out of our fossil fuels to move away from it. Nuclear could be scaled up to power the bulk of our energy for the entire planet. But again, just to give you a sense for scale, to get to that type of a scale, you would have to build a new nuclear power plant every day, starting today from the year until 2050. And we haven't built one in a while here. So it's unlikely that we're going to scale it up that much. And then you have all the renewables here. And you'll notice that they're not all the same size. Not all energy sources were created equal. So renewable energy is great, but there are limits to how much you can effectively get. So geothermal, I understand you had a talk on geothermal from the director of the geothermal office in this series previously, Lauren Boyd. She's great. Geothermal is a great energy source. That's where you're drilling down through the crust of the earth and getting at the heat that's down there and then using that heat instead of burning coal to, for example, make steam and turn turbines and make electricity. It's easy-ish to do where the crust is thin. So Iceland, as I mentioned, gets a lot of its energy from geothermal energy, almost all of its energy from geothermal energy. And there are a few other spots around there where we can do that, but there aren't that many. And there may be some future technologies that allow us to drill a little deeper and broaden that, but it's going to be a small contributor for the foreseeable future. Doesn't mean we don't do it where we can. It just means that we can't turn to that as our panacea solution here.
Real quick, Lauren Boyd said 12%.
Of
if enhanced geothermal works and it's made to be affordable, it might make up 12%.
In the US, yeah. We'll see. We'll see. Okay, so what does the box look like today? Today we use a little bit over 18 terawatts worldwide. So that's an 18.5 terawatt box. How do we fill it today? That's what our energy mix looks like today. It's just another way of showing you what I showed you on the chart of increasing energy use, mostly fossil fuels, with relatively small contributions from all these other sources that you see. But today is what it is. We can't change what we're doing right now. The question is, what is it going to be in the future? My son's 20 years old. What about when he's middle-aged? We're in the year 2050. We need a lot more energy now, right? It's not 18.5 terawatts anymore. Now it's 31 terawatts we need to power the world. So it's a big challenge. It's not just about replacing the current fossil fuel use with renewable. It's actually more energy overall that we need to produce. And the projections, again, look something like this. So everything got bigger because we needed a lot more energy. We're growing them all, but it's actually more fossil fuel use, not less. That cannot be our energy mix in the year 2050. That's existential threat to humanity type energy mix in the year 2050. So let's just play a hypothetical game. And I'm saying hypothetical because I think it's probably not practical to completely use renewable energy by the year 2050. There are folks who disagree with that, but my opinion is not practical to get all the way there in 2050. But let's just say we're going to. I'm going to empty out all those renewable energy boxes. All the wind we can get everywhere, all the geothermal, all the hydropower, et cetera. How much energy is that? It's a lot of energy, but it's not filling up that box. But if you're paying attention, you'll notice there is a box I haven't shown you yet, which is the solar energy box. So how big is that one? Right, so maybe they're not enough. I'm going to move from boxes to circles. That circle, it's just too big to fit on the screen, is the amount of energy that hits the surface of the Earth from the sun all the time. Tremendous amount of energy. You will hear solar energy researchers say sometimes that enough energy hits the surface of the Earth in 1 hour to power the entire planet for a year, which is technically correct, but also not a very useful statement because you can't capture all of the energy hitting the surface of the Earth and use it, right? So what I'm going to do here is like a back-of-the-envelope estimate for what is feasible. What's the size of that solar box? What could you actually get? First thing I'm going to do is throw out the oceans. Really unlikely that we're going to cover the oceans in solar panels for all kinds of reasons. Tossing those out. That's a lot of land area that we just lost, or a lot of surface area that we just lost. Now, of course, you also cannot cover all land with solar panels for all kinds of reasons, not practical. What is a reasonable amount of land that you could actually cover if you really wanted to? I'm going to say 2%. That's still a lot of land, but roads cover about 2% of the land in the United States, for example. So we can do it. We can cover with materials 2% of things, and it doesn't have to be open land. It can be rooftops and other things like that. So that's a much smaller circle now. 2% of the United States looks like that. That's not where we would put them all. I used to put the box in Kansas, and I was talking to some people, these state lawmakers, and they're like, why aren't they in Illinois? So I moved it to Illinois for them. But it doesn't have to be all in one spot. They're spread out. That's just 2% of the area. There's another problem, though. You can't convert sunlight to electricity with 100% efficiency. There are fundamental losses in that process. The laws of thermodynamics limit you to about 30%. You can buy a commercial panel right now for your rooftop that's better than 20%. That's commercially available today. I'm going to be much more conservative. I'm going to say 12%. Very feasible, achievable conversion percentage when you consider that they get dirty, they're not maintained well, the performance goes down a little over time, et cetera. So I'm trying to be as conservative as possible in my estimate here, 12%. No one should argue with that, at least, that it shouldn't be lower. But that little circle, which is a pretty measly piece of the giant one we started with, is that yellow box. So the feasible solar energy supply, what we can actually get, is more than 2 times larger than the total projected global energy demand all the way out in the year 2050. It's an inexhaustible energy supply for the foreseeable future. Now, I do not mean to imply that we should get all of our energy from solar energy. That is not a good idea. But the point is, there's plenty out there from the renewables, in principle, to power the entire planet. Might say, but aren't these things expensive? They used to be. Solar panels used to cost a lot. If you bought one in the 1970s, you were quite the tree hugger. But the prices have plummeted over time. You probably can't even see them in the back, the price. It's so low now for solar panels. It's well below $1 a watt to buy solar panels today. And by the way, the same is true for wind. Wind costs have dropped dramatically since the 1980s. In fact, a lot of people don't realize, but solar and wind are the cheapest form of electricity on the market today in cents per kilowatt hour. So it's not about even mitigating climate change, just straight economics. It makes sense to have more solar and wind. You might say, okay, but what about the fact that these are unreliable, intermittent energy sources? The wind's not blowing all the time, the sun is not shining. Well, it's shining all the time, it's not shining on your solar panel all the time. What do you do about that? Well, one interesting thing about solar energy is that in some sense, the more you have, there are ways in which it helps you out with intermittency. And you can see that from the data here. So if you have one solar array in some spot and clouds are passing overhead, the power output from that array bounces around as the clouds are shadowing those panels. That's a big problem for an operator of the grid. But if you connect that panel array with one that's over here, the clouds aren't over them at the same time. And now what if you connect it to a third and a fourth and a fifth and a sixth and you stitch them all together, it all smooths out to that orange curve that you see there. So intermittency from clouds, as long as it's not overcast across a whole state, can actually be softened by just interconnections between different sources on the grid. Now, to make that work, though, you need to interconnect all those sources, and the current electrical grid can't handle all of that in this future scenario where you have a lot more renewable generation. So it's not just about solar panels, it's also about power lines, moving power around the different parts of the country to deal with where you have extra power and where you have not enough. There is another challenge as you have more solar on the grid, and let me just walk through why that is. So plotted there is a typical look at a demand curve for electricity over the course of a day. It's mostly flat through most of the day until everyone comes home from work or school, and then you get this peak because everyone turns stuff on when they get home. The solar production is just sunrise and sunset. Those two things are not lined up with each other, the two peaks, right? So as you have a whole bunch of solar production on the grid, you're actually producing more than you need in the middle of the day, and right when the sun is setting, it's the worst time. Like, Mother Nature, why'd you do this to us? That's right when all the demand is skyrocketing, right? So it's terrible timing for grid management. And you get this wicked-looking demand curve, apparent demand curve, which for grid operators is a huge problem. This is such a problem it has a name. It's called the duck curve. If you squint your eyes, it looks a little bit like the profile of a duck. I didn't name it, but that's what they call it. This has gotten so bad now in places like California and Hawaii where there's a lot of solar that the shape of the curve is now, it's called like the canyon instead of the duck curve because it just bottoms out in the middle and then has this huge rise again afterwards. How do you deal with this? Storage is how you deal with this. You just got to shift that curve a little bit from the solar production. You got to take that extra power, stick it somewhere when you're not using it, and then get it back when everybody comes home from work and from school. And nowadays, at least at the utility scale, almost all of these solar systems are solar plus storage. And you're seeing it with wind energy as well. There's even a great report from the DOE that just came out, Pathways to Commercial Liftoff, on long duration energy storage about how do you deal with longer time scales too, not just that couple of hours from kind of the afternoon to the evening. What about, it's overcast for a week. Now what are you going to do? Or what about winter versus summer? You need longer duration storage. A lot of technologies exist today, but people are working on new ones as well. So you can use batteries. That's what's pictured here, just big, giant banks of batteries. That works for kind of the shorter time scale of hours, if you will. But you can do other things. You can compress air. That'll sit there as long as you need it to, and then it'll turn flywheels to generate electricity when you need it. You can use, this is called the biggest battery in the world. This is pumped storage hydropower. It's basically a hydroelectric plant where there's a reservoir with a bunch of water up at the top, a hydropower plant. You let it go through when you need power, and then it goes down into a lower reservoir. So now you're getting your electricity out. When you've got extra electricity, you just pump it back up again. Really simple idea, great way to get long duration energy storage. There are a few places that do this already, but we'll do more. You can store it thermally. So the sun's energy can also be turned very easily into heat. We all experience that on a hot day. You can store that heat and then use it to make electricity later in basically giant coffee thermoses that are insulated and can hold that heat for long periods of time. You can also convert it into chemicals. Take the sunlight, use that electricity or the heat or some combination, and make something that can be a fuel that can be used later. And of course, that can be stored basically indefinitely. Lots of ways to store. Okay, important point though. This is where our greenhouse gas emissions come from in the United States. Globally, it looks slightly different, but roughly the same. As we have more renewables and nuclear, these low carbon sources, we're going to take a big bite out of that slice of greenhouse gas emissions right there, the electricity production. And we're also going to take a bite out of transportation as we have more and more electric vehicles, because now the power is coming from electricity. That's great, but it's not everything, right? What about the rest of the transportation sector? The big things like passenger planes and marine transport and rail and heavy-duty road or off-road type transport, those things are not going to run on batteries anytime soon. Maybe someday, but not soon enough. They need fuel. They need high energy density for these types of transport, so you're not going to electrify them anytime soon. What are we going to do about those? And what about all this stuff over here? You guys seen The Martian?
In the face of overwhelming odds, I'm left with only one option. I'm going to have to science the out of this.
That's what we're going to have to do, is science the out of this. So how do we address these other sectors, the hard to decarbonize ones? So residential and commercial, most of that greenhouse gas emission is coming from climate control, HVAC. So right now that's coming from burning fossil fuels or other sources that have carbon emissions. We need to electrify that. Heat pumps are a great technology for doing this. Heat pump technology works really well. There are still some development to do. We're going to need some more research and development to be able to apply these everywhere economically. Industry, huge carbon emissions from things like steel production. That's because we use coke, not coke, but coke from coal to generate the heat and to do the reduction of the iron. We need to electrify that so that the electricity can be coming from low carbon sources. So new ways to do heavy industrial processes like steel production. What about all those parts of the transportation sector that we can't electrify and need fuel? The fuel doesn't have to be petroleum-based. We can use alternative fuels, low carbon fuels that are made with renewable energy. It can be biofuels, that's one approach, so-called sustainable aviation fuels made from growing crops and converting it into basically jet fuel. Or it could be hydrogen is a great one, which can be used either in fuel cells to drive transport or essentially combusted as a fuel as well. Ammonia is another one people are talking about. These are all chemical fuels that can be generated using renewable energy and can power all those other forms of transport that are difficult to electrify. And then another kind of nasty one to deal with is cement. Huge carbon emissions come from the production of cement, and there are lots of smart people working on this one, coming up with new ways to make cement that some of them, not only do they reduce the carbon emissions, they're actually carbon negative. They actually trap carbon in the cement. So I'm excited about some of the technologies that are coming out of that space. This is my last slide. I like this picture. This is an actual photograph of the Earth, obviously taken from space, right as the sun is peeking up behind the edge of the planet there. And that blue line you see is actually the sun illuminating the Earth's atmosphere. And when you see it at this scale, it shows you just how thin the Earth's atmosphere is relative to the planet. It's hard for a lot of people to think, how did we actually change the atmosphere, the chemistry of the atmosphere in a significant enough way that it changed the entire temperature of the planet? Because it looks huge. You go outside and it's like the sky looks infinite, right? You can see it's not actually that big. It is this skin of a peach surrounding the planet, and it's protecting us from a really nasty environment out there in outer space. We've screwed up that skin of that peach, and it's time we do something about it. So with that, happy to answer any questions you may have.